have Trip come up and talk to us about the refrigeration system. What? Yeah, Tim after. Yeah, I have it as first, and so I'm giving him more time.
Okay. My name is Joseph, or you can call me Trip. The experiment that my group is going to be running next week is going to be the refrigeration experiment. So I'm just going to tackle the objectives of this experiment like straight away. We want to be able to perform a thermodynamic analysis of a heat pump, as well as be able to measure the coefficient of performance for that heat pump, and then be able to describe the vapor compression cycle using a pH diagram. And then we're going to be running 2 tests in this experiment to do that. And in those 2 tests, we're going to want to determine the inlet power, the produced heat, coefficient of performance, and then as well as the vapor cycles in a pH diagram, and compare those diagrams with an actual ideal cycle. So this is a Ebeden TR-CDC rig. This isn't exactly the one we're going to be using in lab, but it's kind of more in detailed one, where it has you have your compressor here, condenser, your expansion valve up there, as well as your evaporator. This is how most refrigeration cycles are going to look like or set up. The next slide. So now this is the actual rig that we're going to be using, and kind of as the components names tell you, the main 4 functions are going to be compression, condensation, expansion, evaporation, and then the working fluid that we're actually going to be using is going to be R134A. All right, so more in detail of the actual apparatus components. First, we get the hermetic compressor, which basically is just hermetically sealed compressor, so that means there's no leaking happening inside the compressor. And the compressor actually elevates the pressure and temperature of the working fluid. And then from the compressor, it goes into the condenser, where it cools and condenses the working fluid from vapor to liquid form, using a secondary fluid, which in most typical cases is going to be water. And then it goes into a thermostatic expansion valve, which is actually really important for refrigeration cycles. So this controls the amount of working fluid that goes into the evaporator. So it can use a temperature sensing bolt to actually open the valve to determine how much working fluid is going to be going in there. And then lastly, we have our evaporator, which is when the liquid refrigerant becomes from liquid to vapor form, and it actually absorbs the heat. So this process right here is actually removing the heat from the refrigerator. So that's like the inside, we're just making it cold because it's removing the heat from the interior. All right, so here's your basic 4-component refrigeration cycle. And we have 4 main states or locations that are of interest. So we have state 1, which is actually going to be the compressor inlet. And from the state, we can get the enthalpy of state 1. And then from the compressor to state 2, we can get the enthalpy of state 2. Going across from 2 to 3, going across the condenser, get enthalpy of 3. Now for an ideal cycle, we assume going from 3 to 4, it's going to be an isothermal line, so we can assume the enthalpy of 4 equals the enthalpy of 3. Now looking at the TS, PV, and the pH diagram of this cycle, the 4 main cycles we going to be from 1 to 2, going across the compressor, so it's really just compressing the working fluid. And then the work going into the system will just be the differences of these 2 enthalpies. And then we have going across the condenser, so it's going from temperature is getting cool to the refrigerant is actually getting cool and coming into a liquid form. And the heat removing from the system, again, will be the difference in these 2 enthalpies. And this is actually the useful heat transfer of useful performance of the cycle. And then going across the expander, again, we're going to assume from 3 to 4, it's going to be an isothermal line, so the enthalpies will be the same. And then going across the expander and evaporator, my apologies. Again, we're going to look for the heat transfer as the difference of the enthalpies, and that's going to be the heat transfer leaving the system. We get the next slide. So for this lab, we really want to look at the real versus ideal vapor compression refrigeration cycles. So now this is your basic vapor compression cycles, and this is your TS for an ideal, and then your TS for a actual cycle. Or I have to switch. This is the real cycle, and that's going to be the ideal cycle. So the real and actual cycle differentiates based on like the pressure drop across the fluid, as well as the heat transfer to and from the surroundings. And also a main difference between the actual and real cycle is the irreversibilities. For an ideal cycle, you want to assume going across the compressor that's going to be reversible and adiabatic, but in actual case, that's not the case. It's irreversible and non-adiabatic. So there will be a greater enthalpy change, as well as the losses due to friction will cause a greater enthalpy change as well, and actually heat up the coolant. All right, so again, for this experiment, we want to calculate the coefficient of performance for the system. So the coefficient of performance really just expresses the efficiency of the refrigerator. And it's just basically the ratio of work and refrigeration effects. And it's a function of the work between the compressor and the expander. So we can write it in the simple term of beta equaling the QL over the work net. And the refrigeration cycle is a little weird compared to most power cycles, as where the only work really happening to the system is the work going into consumed by the compressor. So that work is converted to the high heat transfer leaving the top of the system and the low heat transfer being absorbed from the interior of the refrigerator. And it can also be written in terms of enthalpies. Okay. And then, so here's just a couple of sample calculations that we're going to be performing on the experiment. I chose a few arbitrary values, and these values would be measured from the system. So we want to find the temperature going into the compressor, or the condenser, the temperature leaving the condenser. So I just chose low temperature of 30 degrees Celsius and the temperature leaving. So this is the temperature of the water, so the secondary fluid, which is actually doing the condensing. So it's absorbing heat from the working fluid and turning it from vapor to fluid form. So we just do here using the Q dot equals m dot C delta T. And we're given an m dot in the lab, which is going to be about 5 liters per minute, which converts to 0.083 kilograms per second. And after doing this, we get a Q dot of around 13 kilowatts. And again, as I said, we want to find the electric power. However, for a refrigeration system, the only work happening to the system is the power consumed by the compressor, which we'll be able to measure with our apparatus. And then lastly, we just want to calculate the coefficient of performance, which again is just going to be beta equals Q dot over the power of the system. So we'll just have beta equaling about 13 kilowatts over 10 kilowatts, which comes out to be about 1.39, which is a little bit lower than your typical beta for refrigerators. We're going to look for just over about 2. So for in the experiment, we're going to want to look for a greater temperature change across the condenser to get us a slightly higher beta. And then with that, is there any questions?
I have one.
Okay.
Go back to, I think 6. Yeah. You said from 3 to 4, it's an exothermal process?
Yes, like for an ideal refrigerator cycle, we want to assume going from 3 to 4 is going to be isothermal, which is not what it says there, but so we want to assume that the enthalpy is going to be about the same from 3 to 4. And when I was reading online, it said isothermal, or reading from the textbook, but I see how that's going to be conflicting with the diagram, so I'll have to look into that.
Okay. It's not isothermal actually.
Okay.
Just constant enthalpy.
Okay.
That's how it's called. The correct. Because from the graph you will see 3
Right,
to
right.
4 it's
Yeah, no, I think you.
So, yeah. You're right with enthalpy being constant.
Mm-hmm.
Well, the temperature should change.
Sure. Yeah, absolutely.
It's probably move from gaseous state to liquid state.
Mm-hmm.
So there'll be a temperature change.
Okay.